So we're on number 5 here. The viscosities of 4 liquid organic compounds are compared by placing liquids in separate identical tubes, each with an air bubble at the top. Okay, the tubes are inverted and the times measured for the air bubble to travel the length of the tube. For which compound does air bubble take the longest time? So take note that viscosity depends on the strength of intermolecular forces. So the stronger the molecular forces, the molecules would stick together more and the liquid flows less easily. So that means it has higher viscosity, and higher viscosity means that the bubble moves more slowly. Whereas for weaker intermolecular forces, it has lower viscosity, therefore the bubble moves faster. So let's analyze the given compounds here. So we're given 4 options. All right, again, the stronger the intermolecular forces means higher viscosity, which means bubble moves more slowly. Then weaker intermolecular forces, lower viscosity, and the bubble moves faster. And also alcohols with the OH group with hydrogen bonding will be more viscous. More viscous than alkanes, ethers, or halogenoalkanes. And among alcohols, let me just write here, among alcohols, viscosity increases with chain length, which has more London forces, and among the alcohols, viscosity increases with chain length and the number of hydrogen bonds. Therefore, the air bubble will take the longest time in the compound with the strongest hydrogen bonding and or the largest molecular size or long chain alcohol. From the choices here, we only have A, B, and C, which are alcohols, and the longest chain alcohol here is letter C. So the answer here is letter C. Since letter D here does not form any hydrogen bonds, and for A and B, the OH group here, they have less hydrogen bonding. So less hydrogen bonding forms compared to letter C. Then for number 6, this question is about the reaction of potassium iodide with concentrated sulfuric acid. Concentrated sulfuric acid. So which of these would not be seen? Misty fumes, black solid, yellow solid, or dense white smoke? Now let's carefully check what happens when potassium iodide reacts with concentrated sulfuric acid. All right, let's start with misty fumes. Misty fumes, these are hydrogen halide gas. Then this is seen with all solid halides plus concentrated sulfuric acid. So that means when potassium iodide reacts with concentrated sulfuric acid, misty fumes are visible or are seen. How about black solid? So for black solid, iodine is formed because hydride is a strong reducing agent. And then reduces sulfuric acid. Therefore, iodine here appears as a black solid. So when potassium iodide reacts with concentrated sulfuric acid, then black solid appears. How about the yellow solid? Yellow solid is the sulfur. This can be formed when sulfuric acid is reduced. Therefore, yellow solid is also visible when potassium iodide reacts with concentrated sulfuric acid. How about dense white smoke? This is ammonium chloride. Yeah, the dense white smoke will be produced by ammonium chloride. Yeah? Produced by ammonium chloride, but potassium iodide does not produce ammonium chloride or dense white smoke. Therefore, dense white smoke cannot be seen in the reaction between potassium iodide with concentrated sulfuric acid. So the answer should be letter D. So that one is for question 6A, and now we're on question 6B. Right, for 6B, one of the reaction products is the gas hydrogen sulfide. What is the change in oxidation number of sulfur in hydrogen sulfide forms? So recall that initially we're given the reaction of potassium iodide and the concentrated sulfuric acid. And one of the products of this is hydrogen sulfide. All right, so in concentrated sulfuric acid, sulfur here, hydrogen has an oxidation number of +1 and oxygen -2. Therefore, sulfur here has an oxidation number of +6. So this is for concentrated sulfuric acid. In hydrogen sulfide, the hydrogen here has an oxidation number of +1. So we can get the oxidation number of sulfur. So this is 2 times +1 plus the oxidation number of sulfur. Okay, so therefore the oxidation number of sulfur in hydrogen sulfide is equal to -2. Okay, now we already got the oxidation number of sulfur in concentrated sulfuric acid, and that is +6 +6. And then the sulfur oxidation number of sulfur in hydrogen sulfide or H2S is -2. But we are asked for the change in oxidation number of sulfur in sulfuric acid. So that change is from +6 to -2. Yeah, +6 from the concentrated sulfuric acid, and then -2 -2 to in hydrogen sulfide. Therefore, the decrease of units here, the decrease of the oxidation number or the change in oxidation number is just -8. So the answer here is negative 8.